Hi, I'm Liam, a design advocate at Google working on material design.
And I'm Jonathan, an Android developer relations engineer at Google.
Android is getting bigger and better with over 250 million large screen devices running Android across tablets, foldables, and Chrome OS devices today. Many developers already build apps that work on more than one type of device, but it's not always easy to create experiences that scale well across different sizes and across the context in which people might be using them. With new form factors like foldables emerging, the need for responsive apps that work well at every size in every context has never been greater. In this session, we'll go over the latest material design guidance for apps that run on tablets and foldables. We'll show you the fundamentals of how content can best fit these varying screens and introduce some canonical layouts and patterns as a starting point for your own designs. We'll also dig into how to implement some of those layouts when building your apps. And more importantly, we'll give you tips on how to structure your app using principles of responsive UI, so that your code remains focused and flexible while allowing your app to smoothly handle any size screen. We're going to be focused on views in this session, so if you're looking for more about building for large screens specifically with Compose, make sure you see our other ADS talk, Building Android UIs for Any Screen Size. Earlier this year, we launched new guidelines on Material.io for large screens, and now we're adding in guidance to help prepare for even more kinds of devices, including foldables. Our Understanding Layout guidance has been expanded to cover the concept of layout containers, which form a framework for thinking about how parts of the UI like navigation, toolbars, and content can be arranged together across screens. Like in this example from the sample app Fortnightly, which provides a well-balanced tablet layout with all the containers described in our guidance contributing to its design. Compositional guidance walks you through how to make the most of screen space, arranging important content and actions across contexts in a way that maintains readability and preserves users' mental models, from scaling to reveal more content like expanded captions and dates, to smaller compositional techniques like how to visually group content and maintain a sense of relatedness in a denser layout. In these examples from Fortnightly, visual dividers are used to contain updated stories, while on the other side of the screen, empty space and typography are used to group news stories from various categories. We also have guidance on how to structure your layout as a series of columns, allowing for more expressive layouts that are defined in relationship to a rational grid. Right now, many apps consider the screen to be one big canvas or column with elements drawn in relation to one another in horizontal and vertical terms, maybe with an overall margin on either side. And this can work in some smaller contexts, but the problems become obvious at larger sizes. Applying a column grid to the layout allows for large screen experiences that are much more thoughtfully and intentionally organized. Experiences that feel more organic to the device and context. Second, columns improve information hierarchy by allowing you to divide the screen into clear regions containing related information and actions. In this example, you can see 3 clear regions, each leading the user's eyes around the screen, to primary pieces or groups of information in the order in which they're meant to be consumed. Finally, and importantly, column grids allow for consistent response across sizes by providing a rational way to think about how content should reflow as the screen gets bigger or smaller. In this example, we can see that each of the 3 main regions reflow to keep their same hierarchy, but fill the smaller screen in a more ergonomic way. Keeping this grid in mind helps you make choices about component behaviors, choosing to swap or alter components across layouts in the ways that make the most sense for the device size and context. For example, bottom navigation can be replaced on larger screens by a navigation rail, which serves the same functional purpose and uses similar visual presentation, but positions the destinations in a more ergonomic way. Full-screen dialogues on mobile can be adapted to simple dialogues on larger screens to maintain the context of what the user was doing. When swapping components, remember that the component switch should serve a functional and ergonomic purpose for the user first and foremost. Finding the right threshold at which to change your UI is an important step in making an adaptive design. So we've defined new breakpoint values that help classify devices into predefined size classes. These are representative of real devices in the market, and they help convert your raw sizes into discrete, standardized groups with which you can make higher-level decisions about your UI. For example, nearly all standard phones in portrait mode are a combination of compact width and medium height. Due to the ubiquity of vertical scrolling, for most apps it's enough to adapt according to width size classes. Soon these size classes will appear as a new API in the Jetpack Window Manager library version 1.1. We've also integrated them into our tooling in the form of reference devices starting in Android Studio Bumblebee, so implementing UIs based on them will be consistent and straightforward, and developers can move away from checking physical sizes or orientation or other signals that are prone to error. As you design and build for different size classes, think about how people are likely to be holding and touching the devices they represent. Being mindful of the device shape and size will allow you to build more ergonomic experiences. For example, on a tablet or even on a large phone, the very top area of the screen can be really hard to reach without fully adjusting your grip. Keep important actions and content in spots where they can be easily reached. Canonical layouts are a collection of approaches to common layouts which should be a big help when designing for big screens. The first is a simple combination of list detail or list grid views with or without a navigation container at the leading edge of the screen where the content begins. A supporting panel or sheet can also be used on experiences that require focused work like docs. A panel can come in from the trailing edge of the screen or the bottom of the screen to assist with tools or contextual controls. Feeds are common patterns often found in news or social apps. This template uses tiles to encourage discovery. The UX is the same as on mobile, opening an item opens a new page, but is more immersive and designed for the larger screen size. Hero apps prioritize content at the top of the screen and utilize supporting elements around and below it. This is fantastic for media-centered apps.
Thank you, Liam. Now let's talk about structuring your app to take advantage of these canonical layouts using the principles of responsive UI. By responsive, we don't just mean having parallel constructs for different screens. Apps should be flexible because they can be resized for a lot of reasons, like rotating the device, or multi-window mode, or folding and unfolding, so the app can transition from one size class to another and back again at runtime. It's important not to think of size classes as totally independent buckets. Apps also need continuity, meaning the user experience won't be interrupted, so they should never lose their place or their data. To make that possible, the app should have a single navigation graph, which is the model for the different experiences in the app and the way the user moves between those experiences. That model shouldn't change based on configurations, and a configuration change like resizing shouldn't trigger a change in navigation. Think of it this way. It would be really strange if your web browser went back a page, or redirected to another page, or change the history altogether when you resize the browser window. Consequently, every destination should be flexible and be able to maintain its state during such size transitions. And this is where our canonical layouts play an integral role. With each destination, you can ask yourself, getting larger, what can I add? And getting smaller, what can I take away? And then choose a strategy that fits. Now, this might mean rethinking your navigation graph a little, especially if you're coming from a phone-centric design. Here's an example where we did just that in an app called Tracker, which is a Google sample that resembles a task management app. At the top level, it has a list of current tasks and a list of archived tasks. And from either of those, you can drill down to a task's details, and from there you can edit the task. There's also a button to add a new task, but actually we just use the edit task destination for that, and the only difference is that all the input fields will be blank to start. So this was our navigation graph before supporting large screens. We decided that both tasks and archive destinations should show two panes if there's enough space. As a result, we can remove the old detail destination. In this model, list and detail fit well together because they contribute to a single experience, which is exploring tasks. In a minute, I'll explain how we can still show the task details on a smaller screen. So now what about edit task? We could try to incorporate it into the two pane destinations, but editing a task is really a different mode of engagement. The user is inputting content instead of browsing. So for that reason, we kept edit separate and chose another pattern for this destination, like this dialog transformation. So this is our revised navigation graph, and each destination can gracefully adapt when the app gets bigger or smaller. You can find this sample on GitHub if you want to explore the code in more detail. Now that we have this context of growing and shrinking destinations, let's look at building a responsive UI. First, we should consider where persistent UI elements like navigation elements are positioned. Following the material guidelines, we can provide alternative layouts according to the width size classes and reposition the navigation where it's most accessible. A bottom navigation view for smaller screens, a navigation rail for medium screens, and a full navigation view for larger screens. Note how these layouts use a width qualifier, -W, and not the smallest width qualifier, -SW. The rest of the space is used for content, where we can apply the canonical layouts. For list detail, we have a dedicated widget in Android X called Sliding Pane Layout. To use it, You specify the layout width for its two children, and at runtime, sliding pane layout will determine whether there's enough room to show them both. If there is, both panes will be at least their desired width. The extra space can be distributed using layout weight, as shown here with the list pane getting 1/3 and the detail pane getting 2/3 of the extra space. If there isn't enough room, then each pane will use the full width of the parent. The detail pane will either be slid off to the side or covering the first pane. You can control the sliding pane programmatically, and this is what it looks like in the tracker sample from earlier. When the user selects an item from the list, we receive that in a Kotlin flow from our view model, we update the detail pane's contents, and then slide it into view with the open pane call. Be sure to check out our page on developer.android.com about implementing two-pane layouts using sliding pane layout. That page covers additional details like integrating with the system back button to slide the pane back. With a feed, we have an immersive layout showing a collection of items, so Recycler View is a great fit. We can make a big impact by changing which layout manager the Recycler View is using. Linear Layout Manager works great in compact width, but at medium expanded width scenarios, the items become overly stretched and distorted. So switching to Grid Layout Manager, or Staggered Grid Layout Manager, or even Flexbox Layout Manager is much more appealing. We can also change the individual item layouts and make certain items taller or wider than others to increase their importance and create a more interesting visual. In hero layouts, we're emphasizing one particular element and rearranging the other supporting elements around it. There are certainly many ways to approach that, but constraint layout provides the most flexibility for this because it offers lots of ways to constrain child elements, both their size and their position relative to other children. So here's a media app where the hero is constrained to an aspect ratio of 16:9, a description panel uses 60% of the width, and another element uses the remaining space. The constraints can be changed and even animated by using motion layout, which is a specialized constraint layout. For supporting panel, anything from a linear layout to a constraint layout works as a container to position the panel. One thing to think about is, when we transition to a smaller size, where should the panel's content go? So there are lots of options, like using a side drawer along the trailing edge, or using a bottom sheet that slides up, or using an options menu. Or maybe that content is just hidden completely.
When designing specifically for foldable devices, there are a few key considerations to keep in mind. First, foldables provide more than just a bigger screen. They also enable different device orientations or postures based on how folded the device is, and how the user is using it. For the purposes of this talk, we'll recognize 3 explicit postures: closed, unfolded, and tabletop. As we'll see later, it's possible to detect other theoretical postures like book mode as well. Just like other large screens, think about how users are likely to hold the unfolded device. Similar to a tablet, there are regions of the screen that are more or less difficult to reach with your thumbs, and having a free hand to roam the screen is not guaranteed. The bottom corners of the device are a safe bet, while the very top of the device, especially in portrait, will likely be out of reach. This means that if you use components like the navigation rail, destinations that are centered or anchored to the bottom of the screen will be easier to use. Also consider the placement of the hinge and how that will impact interaction. Hinges can have a significant tactile difference or even be a physical separation between two screens, so avoid placing buttons and other important actions directly on the hinge area, which can be understood as roughly 48 dips wide on most devices. In tabletop mode, avoid placing UI elements on the hinge altogether, since it will be virtually inaccessible to users in this posture. For layouts, there are 2 main techniques to think about when transitioning from folded to unfolded. The first is expanding a screen. This puts into practice a simple, responsive layout that expands content to fill the screen, generally by expanding the column grid according to the material guidance mentioned before. The second technique is to add a screen. This can be the same approach as a list detail screen or just another panel that functionally complements the main panel upon which you're building. In both cases, according to the guidance at material.io, you'll want to create an 8-column grid that's split across both sides of the hinge area. When adding a navigation container like the navigation rail, the leading edge of the screen becomes compressed to accommodate the container.
Now let's see how we can take advantage of the fold at runtime. Jetpack Window Manager library provides APIs to detect the presence of a fold in your app's window. Any activity can acquire a window info repository, which is what we're doing here inside of onCreate. Then we'll safely collect from the flow of window layout info between the started and stopped lifecycle states. Whenever a value is emitted, we can inspect the display features and look for a folding feature specifically. So we now have information about the fold, and we can apply some recipes to see if the device is in one of those postures from earlier. Book mode will have the fold state half opened and the fold running vertically, and tabletop mode will have the device half opened and the fold running horizontally. Folding feature also has the location of the fold in the window. This is perfect for updating layout parameters when the fold splits your content view, so you can make adjustments like placing a supporting panel on one side or keeping your hero element above the fold. First, we need the location of the content view in our window, which is given by getLocationInWindow. We'll create a rect using those coordinates, as well as the width and height. So now we have the bounds of the view in the window's coordinate space. Folding feature provides the bounds of the fold, and that's already in the window's coordinate space, so we can just check whether the two regions intersect. If they do, we convert the feature bounds to the coordinate space of the view and return it. By the way, if you use sliding pane layout to implement a list detail layout, you'll automatically get support for the book mode. Sliding pane layout will position the panes on either side of the fold as long as both panes fit. If your app has special behavior related to folding states, you're going to want to write unit tests for that. Jetpack Window Manager includes a test rule that can simulate a folding feature during instrumented tests. So for our test using views, we're adding the window layout info publisher rule, along with the activity scenario rule, and combining them into a test rule chain. In the test method, we acquire the activity through the activity rule. We then create a window feature to simulate tabletop mode, and build a window layout info object, and publish it using the publisher rule. After that, we can use Espresso and JUnit assertions to check that our activity properly handles tabletop mode. While we're talking about testing, we know that UI tests can be difficult to manage because certain tests need to run on certain devices. So to help with that, Android Studio is adding support for Gradle-managed virtual devices. You can give this a try with the Android Gradle plugin version 7.1 and later. In your app's build.gradle file, under Test Options, specify virtual device profiles like the one that you normally manage run from Android Studio, like this Pixel C tablet image. Gradle will then create targets that will execute your tests on the specified device. And Gradle can even download the device image as needed. To differentiate which tests are intended for which devices, we'll make a custom annotation, large screen test, and mark our test functions with it. When we run the Gradle command from before, we add an argument for the Android test runner to only run tests that have this annotation. If you didn't use annotations, you could use other filtering options that the test runner has, like running tests only in a specific class. So by combining those features, we can set consistent run configurations for our tests.
Before we end, we have a couple of additional thoughts and resources for you. Large screens present other opportunities for your app to shine besides just making your own content bigger. In multi-window mode, your app can be side by side with other apps. In addition to being responsive, think about how you can make your app more impactful in this mode, like by supporting drag and drop. Little features like that can really boost the user's productivity and help them enjoy using your app. Large screen devices sometimes come with additional forms of user interaction besides just touch. The larger the device gets, the more likely it is that users will start to use keyboards, styluses, mice, gamepads, or other peripherals. If you want to increase the usability of your app for those kinds of situations, plan to support at least some of those other input modes. We have another session called Input for All that has a lot more details, so make sure to check that one out too. With such a diverse hardware ecosystem, it can be hard to get your hands on devices that cover every shape and size. Today, the Android SDK ships with emulator images for foldable devices, and these emulators allow you to change the folding state at any time down to the angle of the hinge. The upcoming Android Studio Chipmunk will also have a resizable emulator, allowing you to freely change the app window size, so now every developer can try out their app in just about any form factor. We've also been working on new tooling in Android Studio to help you support large screens. The new layout validation tool can preview your layouts on reference devices that cover every size class, show you problem areas like text views with long lines, and recommend different UI components for different breakpoints. To round things out, on the Android developer website, we lay out a comprehensive list of app quality guidelines for large screens. These guidelines are broken up into sections, starting with covering basic compatibility expectations, like whether your app supports both portrait and landscape. Later sections focus on supporting all screen types and states, and using specific screen types or states to provide differentiated experiences. We hope you'll use what you learned today along with these new quality guidelines to build apps that delight your users on all kinds of screens, big and small. You can find all the links used in this talk in the video description. Thanks for watching and enjoy the rest of ADS.